if we can detect wiggles in space-time from earlier times, then we can start to get at some of these like deeply fundamental theories, like what caused the Big Bang, did inflation happen?
So I want to sort of start off by asking what led you to the research that you do? What led you to your interest in black holes? You know, what started your career? You know, where was your first interest in science?
Yeah, well, I'm technically an astrophysicist, and what led me into it, I think, is the physics.
Right.
You know, I grew up, let's say, with a more religious story about what the world is, and as a teenager, I started to question some of that. So it left some holes in my understanding, and I guess as a curious teenager, I turned to different regions, but it was opening some books about space, but actually some of Einstein's work,
right,
where I saw, oh, this could be a path, and so I thought, all right, I'm just going to see if I can pursue this some distance. And what I expected was that I would go to university, get a couple of years in, realize it was way over my head, which was to some extent the case, but nonetheless managed to stick it through, and ended up in astrophysics, just as what I feel is the most awesome type of physics.
Right.
You know, partly because it's all very big, but partly because we get to employ all physics in the study of the universe.
Right. So you studied physics at first, and what was your first interaction with astrophysics? Why is it the sort of most awesome part of the physics world?
I mean, astrophysics is really the physics of everything but this planet. So you really can apply all different fields, whether it's the physics of plasmas, quantum mechanics you need, and on the biggest scale, the physics of cosmology and general relativity, and it's also clearly stitched together in this one cohesive whole when you think about the universe on that scale.
Right. So maybe let's talk a little bit about your research more particularly. So you work on black holes. What for you is the most interesting research that's happening on black holes?
Well, mine, obviously. I actually don't know if that's entirely true. It's the most interesting to me.
Right.
I mean, black holes themselves are wild. They are, they're these places where space and time are pinched, and in a sense that in the black hole, so you have this event horizon, the unescapable horizon where time freezes, and in a sense represents a true boundary to our universe, and whatever's inside isn't in our universe. So philosophically, they're a very strange thing to think about. They're not material in the way that we normally think about things in science, and so that's a draw. The way I get at black holes, I mean, you can't see them, but you can see their effect on their surroundings.
Right.
These intense gravitational fields, and so they, stuff gets stuck in orbit around black holes and energized to extreme degrees. And one example of that is the quasar. So this is a case where you have what we call a supermassive black hole. Okay, you might have a million or a billion suns worth of mass in this one black ball in space, and every single galaxy has one of these, including the Milky Way. Our own galaxy has a 4 million solar mass black hole. Normally they're quiet, no one needs to worry, but occasionally something happens to the galaxy so that the central black hole starts feeding, like gas gets driven in.
Right.
And then you get this whirlpool of plasma that's pouring into the black hole, but on its way in it gets very hot and shines because of that heat, and shines from the ends of the universe. So we see these quasars literally to the beginning of time. We see their light that has been traveling for the entire age of the universe, almost. And so in that light, we have a probe of the history of the universe, of the shape of the universe. They're kind of oddly probes of the universe on the largest scale. And of course, it's cool to try to understand the black holes themselves, which you can do by looking at how things fall into them.
Yeah, I mean, so that brings me to my next question. So one of the things that's interesting about black holes that you were just touching upon is, not only is it, as you say, interesting just to understand how they work, what kind of thing triggers the feeding, as you put it. But also they're a great tool for thinking about cosmology as well, right? So could you tell us a bit, what can we learn from black holes about cosmology, about the beginnings of the universe?
Sure. So, well, let me tell you a little about the specific thing I'm working on at the moment.
Right.
I'm interested in a case of where you see these quasars that I mentioned in a configuration where you have an entire galaxy that just happens to be perfectly along your line of sight to that black hole.
Right.
And so Einstein's theory of gravity general relativity predicted the existence of black holes, but also predicts that that mass bends space, changes the shape of space, and so this massive galaxy acts like a kind of lens. So you have light coming from that distant object, the quasar, bent by the gravity of the intervening galaxy back towards us. And so for us, what we see is not what's there. We can see, for example, a galaxy with multiple images of the same quasar viewed through different paths through space.
Right.
So these are gravitational lenses, and they are an incredible laboratory. We can use this sort of extra galaxy-sized mirror on our telescope to study the inner regions of the quasar and learn about the quasars and the black holes themselves. But we can also learn about the universe, because these are paths through much of the universe. Okay, the most distant gravitationally lensed quasars, their light has been traveling to us for many billions of years, and it's been traveling through an expanding universe. One of the biggest questions in the field right now, not just astrophysics but cosmology, is why is the universe not just expanding, but why is that expansion accelerating?
Right.
Okay, so we have this thing called dark energy, which is causing an accelerating expansion of the universe. We don't know what dark energy is, we just know it's there. And part of the difficulty in understanding what it is measuring the exact effect. So the current results, which are, there are sort of two types of results. One is looking at exploding stars, supernovae, which allow us to sort of get distance measurements out to a certain distance. And the supernovae let us track the expansion history of the universe over the past, several billion years.
Right.
And the other thing that we look at is light from the very, very, very early universe, the so-called cosmic microwave background. That's this afterglow of the Big Bang. And by studying that, we can also get another measurement of the subsequent expansion history of the universe.
Right.
So we have these two principal ways to measure the expansion history of the universe, and they're in conflict. So the results from the supernovae give us one number for the expansion rate, and the cosmic microwave background gives us another number, and they're close, but they're not close enough.
Right.
So so one of these groups is doing something wrong, or the expansion history has changed in a way that our current models of dark energy don't understand.
Right.
And so one thing that we really want to be able to do is map that expansion history, map how fast the universe has been getting bigger and how that expansion rate has changed over cosmic time, and get a history of that change, because that history could really tell us what, it could tell us, I say what dark energy is, but it could at least tell us what family of thing dark energy is.
Right.
And so this gravitational lensing, when you have these different paths through space, you can use them as rulers, essentially, to measure the distances, and so get sizes for the universe at different stages through its history. And the way we do that is so cool. I'd like to tell you if I can.
Absolutely.
It's that these different paths that the light takes around the galaxy towards us have slightly different lengths. Okay, they're not perfectly symmetrical. And if you can measure the difference in lengths, then you can. It all falls together. You can get the distance to the lensing galaxy, you can get the distance to the quasar.
Right.
And so all you need to do is measure the lengths of those paths. And you can do that because those distant sources, those quasars, are not very stable. Okay, so we're talking about a bunch of stuff falling onto a black hole, fueling. And so they're very violent, energetic things, and so the light fluctuates as the fueling goes up and down, as who knows what happens. And so we see this sort of fluctuation signal. And so if you remember these multiple images of the same quasar, each one is fluctuating. And the fluctuations are correlated but offset in time from each other.
Okay.
And so if we can line up those correlations, then those fluctuations, then we actually get the lengths of those paths, and we can get this independent measure and hopefully figure out which of those teams was right, if any of them.
Right. Or perhaps maybe a third team yet to be invented.
Exactly.
Right. So let's turn now to some of the work that you've done in communicating scientific research alongside your own research as a scientist. So the first question I have is, how have you found the relationship between being a researching scientist, an astrophysicist, and being someone who puts a great amount of care and work into communicating with people who aren't formally trained as scientists? I mean, have those two practices mutually informed each other? Do they sometimes pull in tension? How does it work?
Yeah, the answer is yes. They do both.
Right.
We'll start with the negative. So, I mean, firstly, it takes a lot of time.
Right.
And, so the time constraint is the big thing. You know, you want to do a great job in both, but something has to give somewhere. So I think I would be better at either if I only did either.
Right.
In some respects, it used to be that people who spent a lot of time in science communication were frowned upon in academia.
Right.
For example, I think Carl Sagan was not widely respected in his field of astrophysics, planetary science, for his outreach work. But I also think that he sort of changed the game, particularly in astrophysics. I think now it's seen by many as an honourable thing to do, and that's why there are more astronomer science communicators than anything else. We're all just trying to be a little bit more like Carl Sagan, but there's more benefit than that. There is something really valuable about expanding your breadth of understanding of the world, and certainly of science and scientific fields. I think science is now a hyper-specialized endeavor. To make any progress, to chip away at the boundaries of our now large continent of knowledge, you have to really get into something with extreme specificity, and that's often done at the expense of having any breadth, and that's a mistake, I think. I think there's so much to be gained from crosstalk between fields, and so with PBS Spacetime, we've now done well over 300 episodes, and we've spanned much of physics, and I can't say that I remember everything that we've ever talked about, but there has been some kind of, broadening of my perspective, and I feel that it helps my science. I'm now working on some areas in quantum mechanics, for example, that I never would have imagined working on before, and I've got into some really interesting machine learning projects that I think have also been helped by just seeing that so much crosstalk is possible between.
Yeah, I mean, and also I suppose a sort of game-changing resource is being able to share video content that you've put a great amount of effort in just across the world, right? I mean, so. How have you found, what's been, in your opinion, the best way to engage with this public outreach-based work? I mean, you do video work, but how have you found writing public communication of science? How have you found presenting it live? What's your sort of preferred method, do you think?
Presenting live is more fun.
Right.
Because you get that immediate feedback and engage.
The claps.
And you get to love the claps.
Love the claps.
It's more like the conversations you can have afterwards, and just the feedback from people's faces being right there. It's actually quite it's a skill I had to learn to be even human seeming when I'm talking to this blank screen of the camera and pretending that I have to literally pretend that the camera is someone I know that I'm talking to in order to, I guess, not be entirely robotic. It's tricky. So the live thing is best. I write the scripts, and so I sort of have the that writing side of it, and
Right, yeah.
and I think that's my best medium for getting the ideas out is through the pen.
Right.
Then I just say the words. Which,
Right. Right. Okay. Well, so maybe let's turn to a sort of future looking more broadly. What do you think is going to be the next paradigm shift in physics, or maybe astrophysics specifically, the next discovery, theory, idea that's just going to change the way people think about what they're doing?
So the next big paradigm shift I feel like we've had a series of paradigm shifts in astrophysics recently,
right,
including and maybe predominantly the first detection of gravitational waves.
Yes.
Okay, it's opened a massive new window, and as we get better at that, as we build LISA, which is going to be the space-based gravitational wave observatory, will detect a whole new family of phenomena. Things like this may help us push back our view to earlier and earlier times, which are currently limited. Currently, the telescopes that we build can see back to about 400,000 years after the Big Bang.
Right.
Prior to that, the universe was opaque to light, and we can't.
Right.
It's like there's a brick wall, but not to gravitational waves. And so
Right.
if we can detect wiggles in space-time from earlier times, then we can start to get at some of these like deeply fundamental theories, like what caused the Big Bang, did inflation happen, all of this wonderful stuff. So that's one side. The other thing in astrophysics that's going to change the world in a way that will resonate more with the average person is when we learn to see the atmospheres of Earth-like planets around other stars.
Right.
And we know how to do it. Okay, we know how to build the type of telescope, the type of interferometer telescope in space that will be able to detect the chemical signatures in around planets around other stars. And that sounds technical, but what you're seeing is whether those planets have biospheres. And so the first detection of life will be when we learn to see those planets, and we know how to do it. We just need to spend the money, and it will hopefully happen in our lifetime. But when we find for the very first time that one other planet in our galaxy has life, that changes the game completely. Yep. It changes all of our thinking about the abundance of life and the uniqueness of humanity, etc.
Yeah. Well, no, that would be a game changer. I mean, so speaking of spending money, if you had completely unlimited funding, I mean, maybe you've just answered this question. What would you choose to spend it on as a physics experiment, or as a design for part of some research?
Yeah, that's it.
Right.
I would, it's not even my direct field, but I think it's more important.
Right.
I think it's important for us to understand what our place in the universe is. It's nice to understand what the universe is, how it began, and so on, but understanding what we are in the universe is just, I mean, it could save our species to develop our global perspective in that way. Yeah. So developing these orbiting atmosphere detecting telescope arrays would be the first. You said unlimited funds, so that's where I'd start.
That's where you start, okay.
Then I'd build probes to go there.
Yeah, brilliant. And so so you said that we can already, as a technical matter, build all of the equipment. So what is standing in the way of this kind of research happening right now?
Congress,
right.
So politics.
It's political.
The amount of money that gets to be spent by NASA or ESA or whoever.
Right.
But I mean, we're making progress. We are. So the James Webb Space Telescope can do this, but not for what we call terrestrial planets, not for Earth-like planets yet. It can do it for larger ones that are less likely to have what we call biosignatures in their atmospheres. I mean, with all science, it's always, you take baby steps, you do proofs of concept, and so the Webb is a proof of concept in that regard.
I see, right.
But it's also a generalist telescope. It's not specifically designed to do that.
Right.
And so right now what's standing in the way is just collective will, political will.
Right. Yeah, brilliant. And so for our final question, what are you working on right now for your public communication? What content are you working on at the moment?
So I work with PBS, Digital Studios in particular, on a YouTube show which is called PBS Space Time, and it releases, I think we're 3 a month officially,
right.
A fair bit, most weeks. And it's a short show. It's like 10 to 12 minutes where we tackle different topics across physics. Okay, we started with space, but now we do all physics. And I think the thing that we're known for, if we have a thing, is that we're not very shy about digging deep.
Right.
And that was a risk, because I think the standard wisdom is, all right, everything must be super accessible to everyone listening to it. But we found that our audience, and in fact I think many or most people, are really hungry for a deeper bite, for a sense that they're not being talked down to.
Right.
People are very sensitive to that.
Right.
And are also patient if, when things get a little bit technical, as long as you're not being, obfuscatingly technical, I think you can. So that's what we're doing right now.
As long as they feel that you're taking the time to engage with the technicality as a matter of communication and education, and not as a matter of just shrouding the world that they're sort of not invited to be a part of.
Yeah, and there's only so much that anyone can take out of a 10-minute YouTube video.
Right, of course.
We can't explain string theory, but we can give people a more real feeling for what string theory is.
Right.
And we sort of think of these programs as seeds, as starting points for the curious to take off from.
Yeah, brilliant. Well, I think that's all we have time for, but Matt, thank you very much for coming down.
Absolute pleasure. It's wonderful to be here.
Brilliant, thank you.